Okay, so this will be the first lecture over NMR spectroscopy. So we're going to spend a lot of time going through the basic theory of NMR, which is much more complex than the basic theory in mass spec and IR spectroscopy. So hopefully pay attention, and hopefully I do a good job of trying to explain this theory to make it understandable. So first of all nuclei carry a charge because all nuclei have protons in them, and protons are positively charged, right? So in some nuclei, this charge spins on a nuclear axis. So if this is representing a nucleus of the atom and it spins, so the nuclei could be spinning that way, or it could be spinning that way, right? This is one way to think about it. And so because it's a spinning moving charge, all spinning charges have electric fields, and all electric fields have magnetic fields associated with them. So if it's spinning this direction, and right hand rule, so if you take your right hand and wrap your fingers in the direction of the spin, then your thumb will point in the direction of the magnetic moment. So if it's spinning like that, its magnetic moment's in the yellow stick direction. And if it's spinning like this, it's instead the opposite direction. Wrap your fingers in the direction of the spin, then its magnetic moment is in this direction. So depending on how the nucleus is, and of course the nucleus doesn't know how it's spinning, it's irrelevant to the nucleus, but I'm an external reference point, so I can see which way it's spinning, whether it be having from my perspective, a clockwise spin or a counterclockwise spin. And that would change its magnetic moment from either being that direction or that direction. So if it's spinning counterclockwise and you wrap your fingers in the direction of the spin, then its magnetic field would be in that direction. Or if it's spinning clockwise and I wrap my fingers in the direction of the spin, then its magnetic field would be in that direction. Okay, so these two nuclear spin states are equal in energy unless they are in the presence of an external magnetic field. So B is a symbol for magnetic field. So if that magnetic field is in the up direction on the piece of paper, then the two nuclei could either have their magnetic fields aligned with the field, and that's what's called the alpha state, or their magnetic field could be aligned against the field, against the applied field, and that's what's called the beta state. Okay, so this is one of the key diagrams in NMR, trying to understand this diagram. So this would be in absence of an external magnetic field, the two nuclear spin states are equal in energy. In this region, then the nuclei are in the presence of an external magnetic field. So here, it's a small external magnetic field. Here it's a large external magnetic field. So as we move from left to right, the strength of the external magnetic field gets bigger. And so now the two nuclei spin states are not equal in energy. It's lower in energy to be aligned with the field. So that's aligned with B, and this is aligned against B. So it's lower in energy to be aligned with the field, because the magnetic field, of course, is a force. It's lower in energy to be aligned with that force than it is to oppose that force. And so the difference in energy between those two nuclear spin states is given by this equation. This is what's known as the magnetogyric ratio. It's a constant for the different nuclei. So not all nuclei are NMR active. They have to have spin in order to be nuclear active. So we're going to look at several nuclei. We're going to look at mainly two, proton and carbon. So carbon-13 and proton hydrogen-1 are both NMR active. Their nuclei have spin. So we'll look at other nuclei. Fluorine-19, for example, is NMR active. So there's lots of nuclei that are NMR active, but not all nuclei are NMR active, because not all nuclei have spin. But this is a constant for the different nucleus. So proton would have a different value than carbon, which would have a different value than fluorine. And then H is Planck's constant. B0, B naught is the strength of the applied magnetic field over 2 pi. And so again, the bigger B is, the bigger the difference in energy is between the two nuclear spin states. It requires more energy to oppose the field than align with the field. Okay, so to illustrate the basic principles of NMR and how you get a signal out of NMR, so let's just say you had 5 nuclei. And in the absence of an external magnetic field, they would be orientated in random directions, right? They could be like that, or like that, or like that, or like that. They could be spinning clockwise or counterclockwise, and they could be all random orientated. But then when you put them, so if we put the external magnetic field in this direction, then the 2 nuclei, so if it's spinning like that, would be against the field. If it's spinning like that, would be with the field. So the 2 nuclei could be aligned with the field, or the 2 nuclei could be aligned against the field. So spinning that way or spinning that way, right? Okay, so when you apply the external magnetic field, then some of the nuclei and the majority of the nuclei would be aligned with the field, but the difference in energy between the spin state is not that big, so there will always be some nuclei aligned against the field. So what you do then is you apply an energy source. And as we'll see, this is radio frequency. So we basically apply enough energy to make the nuclei do a spin flip and go from being aligned with the field to being aligned against the field. So we apply whatever this energy gap is, whatever delta E is, we apply that energy, and then that will cause what's called a nuclear spin flip. So the nuclei would be going aligned with the field to all be in, so this would be what's called an excited state. So then they would all be aligned against the field. And so we could measure that energy difference when they absorb the energy, but in NMR what's done instead is, so now if you remove the energy source, then what's going to happen? Are all of the nuclei going to stay in this excited state and be aligned against the field? And the answer is no. Some of them are going to relax back, or they're going to decay and do another nuclear spin flip and go back to the original state. And so that's actually what's measured in NMR, is measure the energy that's given off. And so you return to the original, so you turn off the radio frequency generator, and then the nuclei will go from being aligned against the field to the majority of them being with the field, and they'll give off that energy, and that's what you measure in NMR. Okay, so yeah, so again, you could measure the energy absorbed, or you could measure the energy released, and that's, so if we call this, step 1 would be applying the magnetic field, and then that's going to create this difference in energy between the spin states. And then step 2, you apply a radio frequency, and so the nuclei absorb energy and be aligned against the field. You could measure that if you wanted to. And then step 3, you turn off the radio frequency generator, and energy is given off, and nuclei go back to their original state, and that's what you measure in NMR. Okay, so of course, if you remember this equation and these equations from General Chemistry 1, E is equal to h nu. So energy is related to frequency, and frequency is related to wavelength through the speed of light. So if you know the energy that's emitted, then you know the frequency of the radiation that's emitted. And if you know the frequency, then you can know the wavelength of the radiation that's emitted. Okay, so what's going on inside the box? So how does basic NMR work? So this is basically what the instrument rough sketch looks like. So you have 2 big magnets in blue. and they have their own magnetic field, which is what these blue lines going across are representing. That's the magnetic field lines, or the magnetic flux lines of the big magnet. And then you have your NMR tube, and that sets down in between those magnets. So you have the two big magnets, and you put your NMR tube down. Well, you have the big magnet, and you put your NMR tube down within that magnet, and those magnetic flux lines are going through your sample. And then basically the red is trying to represent a coil that you pass radio frequency through. And when the radio frequency is just right, then you cause a nuclear spin flip. And the nuclei going from being aligned with the field to against the field. Okay, so if we did the calculations, so if you had a so Tesla is a unit of energy, or unit of magnetic field. So if we had a magnet that could generate 2.5 Tesla, and we did the calculation for protons, so that's this magnetogyric ratio for proton, so 26,753 inverse seconds, inverse Gauss, and then we convert that, so this is just a conversion factor to convert Tesla to Gauss, divided by 2 pi. So basically, Tesla is going to cancel, Gauss is going to cancel, and we're going to be left with inverse seconds. Inverse seconds is a unit of frequency. So if the magnet's 2.5 Tesla, then the difference in energy spin state between being aligned with the field and against the field is 1.06 times 10 to the 8. Inverse seconds, or inverse seconds, if you remember, is the same thing as a hertz. So then if we just convert 1 megahertz is 10 to the 6 hertz, then that would be 106.4 megahertz radio frequency energy, which would be what's needed to cause the nuclei to undergo a spin flip, be aligned with the field to being aligned against the field. Okay, so NMRs come in different sizes, which means basically they can different magnetic fields. And of course, what that means is they cost different amounts of money. So you can have a magnet that is 1.4 Tesla. You would need about 60 megahertz radio frequency to cause nuclear spin flips. Or 2.5 Tesla, so of course as the magnetic field gets bigger, you need higher frequency radiation, more energy to cause nuclear spin flips. Right, that's what this diagram again indicates. As you go to bigger magnet, the energy difference gets bigger, so you need bigger, higher frequency to cause the nuclear spin flip. 4.7 Tesla, so as you double the magnetic field, you double the radio frequency required to do spin flip. So A&M Commerce has 2 NMRs. We have a 400 megahertz NMR, so its magnetic field is 9.4 Tesla. We use that for research purposes. And then we have a 60, well actually we have a 90 megahertz NMR, which you use in the teaching lab. Okay, so but anyway, the point is different NMRs basically have different magnetic fields. And so 500 megahertz, 600 megahertz NMR, so the top of the line NMRs can have 21.5 or 23.5 Tesla magnets. So 900, that would be a 900 megahertz NMR or a 1 gigahertz NMR. And so of course as the magnetic field gets bigger, generating those magnetic fields, the cost of the instrument gets bigger. So 60 megahertz NMR cost about $60,000. 400 megahertz NMR cost about $400,000. Yeah, so how do you buy a $400,000 instrument? It's pretty expensive. So NMR is a very expensive technique. It costs a lot of money just to buy the instrument. So you write research grants, National Science Foundation, for example, and try to get funding to buy an instrument. Then if you get to the really top of the line instruments, these instruments cost about $5 million. So pretty pricey. So not everybody has a 1 gigahertz NMR, and To the best of my knowledge, there's only 2 in the world. One of them was in Europe, and one of them was at the Scripps Research Institute in La Jolla, California. So we'll talk a little bit later about why would somebody want to spend $5 million or need to spend $5 million on an instrument instead of $60,000. So one of the reasons we'll talk about is what's called resolution. The more powerful the magnet is, the better it's going to separate the peaks out, and the easier it is going to be able to interpret your spectra. Okay, a little bit more detail about what's inside an NMR. So if the blue is representing the magnet, well, so any magnet over 100 megahertz requires a superconducting right. To get those type of magnetic field strengths, you need superconducting magnets. And how do you get superconducting magnets? You generally need very cold temperatures. So we had to keep our 400 megahertz NMR, since it's superconducting magnet, we had to keep it really cold. So we keep the magnets bathed in liquid helium. So liquid helium has a boiling point of negative 269 degrees Celsius or 4 Kelvin. And to keep the liquid helium cold, we use liquid nitrogen. So liquid nitrogen has a boiling point of negative 195 degrees Celsius. So one of the reasons the NMR instruments are designed like this, because liquid nitrogen is pretty cheap. A gallon of liquid nitrogen costs about the same as a gallon of milk, but we use a lot of liquid nitrogen. We have dewars that are about this big and about 6 feet tall or 5 feet tall, and we use one of those dewars every single week. We have to fill the instrument up with liquid nitrogen, and we had to fill it up. Liquid helium is much more expensive. We had to fill it up with liquid helium about 4 times a year. So in all, to keep the magnet superconducting, they must be kept very cold. So that's what we use the cryogens for. And that cost itself, just the cryogens itself, cost about $20,000 a year, just to keep the magnet cold so that it's superconducting. So the NMR is a very expensive technique, but it's a very powerful one, generates tremendous amounts of information. But the instruments cost a lot of money, and once purchased, it costs a lot of money just to buy it, costs a lot of money to maintain it. So every single day, 24 hours a day, 365 days a year, that magnet has to be kept cold. If it ever warms up, it undergoes what's known as a quench. It loses its superconducting capabilities, and so if you want to re-energize the magnet, it costs about $20,000 to $40,000 to do that. You have to hire an NMR engineer to come out. NMR engineer is going to cost about $300 an hour. So it gets pretty pricey. If you ever have problems with your NMR, it can be a very expensive problem. Okay, so that's some of the basic theory of how you get a signal in NMR. And now let's talk about where the signal is going to occur at the different frequencies. So if you just have a proton, so proton's not very interesting. It has no electrons. And so if you apply an external magnetic field, it's going to fill 100% of that magnet because there's nothing to shield it from the magnet. But H plus is not very interesting. It's more interesting to look at molecules where hydrogens are attached to something, like carbon, for example. So if a hydrogen is attached to carbon, then you have a CH bond. What is a CH bond? It's 2 shared electrons, right? So electrons are moving charges. Moving charges have electric fields. Electric fields have magnetic fields. So electrons have their own magnetic properties. And so when you put this molecule in the presence of an external magnetic field, then that will induce a field, a magnetic field from the electrons. And so these red arrows represent what the magnetic field lines for the electrons in the CH bond looks like. Okay, so this is basically just tries to explain all of this. So the red lines are the magnetic field lines of the electrons in the CH bond. So because of the distance of a CH bond, so hydrogen just happens to lie in a region of space. So if you notice, that arrow is pointing in the opposite direction of this arrow. So the magnetic field lines of the electrons in the bond, hydrogen is in a region of space where the induced field from the electrons is in the opposite direction of the applied magnetic field B. And so basically what that's going to do, it's going to shield the hydrogen from some of B. So the hydrogen's not going to feel all of the magnetic field that's being applied. So you can think of that as like these two are going to cancel each other out to an extent. So since they're in opposite directions, they won't totally cancel out because B is a lot bigger than the magnetic field lines from the electrons, but it will cancel out a little bit. So hydrogen's not going to feel the full effect of the magnet. So what that means, if you don't feel the full effect of the magnet, right, B is a little bit less, and if B is a little bit less, it's going to require less energy to do a nuclear spin flip. The bigger B is, the more magnet is filled, the more energy is going to be required to do a spin flip. So if you looked at this in an NMR spectrum, for example, so this is what a typical NMR spectrum looks like. You have peaks or signals. And so some terminology for NMR. The left is what's called the downfield region. The right is what's called the upfield region. The left is the high energy region. The right is the low energy region. The left is said to be deshielded, and the right is said to be shielded. What is it shielded from? It's shielded from the magnet. All right, and so the point is, again, is that the magnetic field lines from the electrons in the CH bond shield the hydrogen from some of B. So it's going to require less energy for this to do a nuclear spin flip, so it's going to be at a lower frequency or lower energy. And this is going to require more energy since it fills more of the magnet. It's going to require more energy to do a spin flip, so higher frequency. So the horizontal axis in NMR is basically increasing frequency required to do a nuclear spin flip from right to left. And where the signal occurs at is what is called chemical shift. Okay, so when you see a signal in NMR, basically what is happening is the nucleus is doing a spin flip. It's going from being aligned with the field to against the field. Okay, so what factors affect chemical shift? And that would be the induced field from the electrons in the bond around hydrogen. Okay, so if we took these 5 molecules, which one is going to require the most energy for a hydrogen to do a nuclear spin flip? So if we're doing hydrogen NMR, so every single hydrogen in a molecule can do a nuclear spin flip, so you would see a signal for it. So this molecule you would not see in proton NMR because there's no protons on it. There's no hydrogen, so there's not going to be a signal. But the other 4 molecules have hydrogens, so when the radio frequency is just right, the hydrogens will do a spin flip and go from being aligned with the field to being aligned against the field. Okay, so if you apply a magnetic field, well, so which of these induced fields, that one, that one, that one, or that one, is the biggest? And that's going to depend on how much electron density is in the CH bond. The more electron density, the bigger the field from the electrons. And the field from the electrons is opposed to the applied field, right? So now if you apply a magnetic field, so that induces these, the red fields. And the point is, so what do you know about chlorines? So chlorines are very electronegative, right? So the chlorines are going to be pulling electron density out away from the hydrogen. So if you reduce the electron density in the CH bond, then that's going to make the field from the electrons smaller. And so that means if this is smaller, it fills more of this, right? Since there's no chlorines on the right for CH4, then this is going to be bigger. So if this is bigger, it opposes B, so H fills less of the external magnetic field. So which one's going to require more energy to do a spin flip? It's going to be the hydrogen that fills more of the magnet. And so it's going to be the hydrogen where the electrons in the CH bond have been removed. Right, so the CHCl3 hydrogen is going to fill more of B than CH4 is, because the electrons in the CH bond, there's more electron density there. They're going to have a bigger induced field that's opposed to the applied field. Okay, so if you did the NMR of these four molecules, it would basically look like that. So this requires more energy. And this requires the least energy. To spin flip. So this is going to be at a lower frequency or a smaller chemical shift, and this is going to be at a higher frequency. Or, right, this hydrogen is shielded from the magnet from the CH electrons, and whereas this would be deshielded. It's going to fill more of the magnet. Okay, so the more chlorines there are, of course, the more electron density is going to be removed from the CH bond, and then the hydrogen is going to fill more of the magnet, since there's not as much induced field to oppose the applied field. Okay, so in NMR, there's three basic concepts to understand. One is the chemical shift, which is what we've been talking about. So that's the frequency where the nuclide resonates at or does a spin flip at. And then other two concepts are what are known as integration and splitting pattern, which we'll talk about in the next lectures. So in chemical shift, there's two main factors that affect chemical shift. We've been talking about electronegativity, and in the next lecture, we'll talk about pi systems as well. Okay, so it's pretty complex theory, and there's a lot more to go, but hopefully what we've talked about so far makes sense.